Hello, everybody. Good morning, good afternoon, good evening, wherever you are in the world. We are happy to have you here on this webinar here in December. We're very excited to get started. This has been a long time coming webinar, so without further ado, I'd love to introduce our speaker today, William Fatigante. William Fatigante is an application scientist within the Applied Markets Division here at Bruker, concentrating on DART-related applications. William received his Master's of Science from the Illinois State University, where he focused on applying ambient mass spec methods for forensic evidence and screening and confirmation. Now that he's been with Bruker for over a year, William has learned the ins and outs of DART-MS and its potential to provide a rapid screening solution to the ever-changing, ever-evolving challenge of PFAS analysis. So without further ado, William, I'll hand the virtual microphone over to you and we can get this exciting presentation started.
Awesome. Thanks for the introduction, Megan. And I myself would like to welcome everyone who's joining us today. So during today's event, I'll talk about the chromatography-free screening of PFAS through the use of SPME-DART mass spectrometry. This was a previously presented presentation at the annual American Society for Mass Spectrometry conference back in June. And so we decided to bring it to you all live for those who could not attend this year. So a quick overview of today's webinar. We're first going to start off with a quick introduction to PFAS and their ongoing challenges. We're then going to talk about the hardware for today's experiment. That's going to be DART technology as well as the mass spec being used. And then followed by an explanation of SPME and the overall experiment workflow, and then discussing the results of the experiment. From there, we're just going to wrap it up with some concluding thoughts, and any remaining time we have, we'll be happy to take some questions. As by now, I'm sure most of you watching are well versed as to what PFAS are and the potential dangers they pose. But just as a quick refresher, PFAS, or per and polyfluoroalkyl substances, are fluorinated hydrophobic carbon chains that are attached to various functional groups. So as we can see here, we have a few examples. So we have PFOS, PFBA, PFOA. As we can see, all of them have a long carbon chain that's fluorinated on all sides. The only thing really different between these is the functional group that it's attached to. So these are human-made chemicals that have been widely used since the 40s. So they've been used in various industrial and consumer products due to the unique water and grease resistant properties. And again, those properties stem from the fluorinated carbon chain that's around the molecule. These can be found in a wide range of products, including firefighting foams, nonstick cookware, waterproof clothing, food packaging, and cleaning products. So because of how well they worked, they were readily introduced into our into our consumer goods and into our lifestyle. So these are extremely stable compounds. They don't break down easily in the environment, earning them the nickname, as most people may know them as, is forever chemicals. And now studies have been coming out linking actually PFAS exposure to various health effects, ranging from liver damage and thyroid disease, all the way up to increased risks of certain cancers. So between that and the costly and complex remediation process of PFAS contaminated sites, these two effects have kind of brought PFAS analysis into the limelight for environmental analysis. And the reason why they've kind of been at the forefront of discussions is that the sensitivity required for testing is in the low part per trillion level. And we may need for even greater sensitivity in the near future. So the U.S. Environmental Protection Agency, they set these health advisories on known or anticipated contaminants that occur within drinking water. And below we have a list of some of the lifetime health advisories on 4 different PFAS compounds. So back in 2016, they reported for PFOA and PFOS health advisory limits of 70 parts per trillion. And in more recently, in 2022, they actually severely decreased that limit down to 0.004 part per trillion for PFOA and 0.02 parts per trillion for PFOS. And even adding, 2 other compounds, Gen X chemicals, so it's a kind of a designer class of PFAS compounds. So they have a health advisory limit of 10 part per trillion, and as well as adding PFBS to the list, but having a health advisory limit of 2,000 parts per trillion. So at the time of publishing, the EPA made note that current analytical methods can detect Gen X and PFBS at these health advisory levels. But however, for PFOA and PFOS, our current technologies, cannot really hit these these low levels that they're putting forward. So therefore, they usually have a minimum reporting level down to the single digit part per trillion level. So in response to the ever increasing need for ultra trace analysis of these molecules, highly sensitive techniques must be developed with increasing focus on higher sample throughput for both screening and quantification of these contaminants. So traditional PFAS screening, commonly relies on HPLC MS applications. So we're using liquid chromatography. So the EPA put forth a method that I'm sure most of us are familiar with, and it's the EPA 533. So this includes an HPLC run of about 35 minutes per injection with a flow rate of 0.25 mils per minute. So while HPLC MS is going to remain the gold standard for quantification, there are some benefits to employing non-chromatographic methods for contaminant screening. And a couple of those benefits including your higher sample throughput, so removing the bottleneck of the analysis, and then greener lab solutions. We're trying to conserve LC mobile phases and produce less organic waste. And then an added benefit of that may be also saving your lab some money down the road too. So the sample screening can provide a potential for leading fewer samples to be analyzed by HPLC techniques. So it's with all this in mind that we began exploring DART mass spectrometry for that non-chromatographic approach. So DART, or direct analysis in real time, has already been implemented and published in a wide variety of areas of interest, such as forensics and food safety, and of course environmental analysis. So in simplest terms, DART is a technology that uses heated ionized inert gas to complete thermal desorption and ionization of chemicals for analysis by mass spectrometry. So your sample does not have to be in solution. You just have to position a small fraction of the sample in the ionization region and can generate ions right off the surface. So it's providing one of DART's biggest appeals, being that sample preparation in most cases is minimal, if not non-existent. So before going any further, I wanted to take a moment to talk about how the ionization process works. So here we have a DART source cutaway image showing and depicting the major components of the source itself. So we're going to start on the left side here at the back of the source. So inert gas is going to flow into the back of the source. This is commonly going to be helium as our ionization gas, but nitrogen could be used as well. So the gas is going to pass a high voltage needle. So that electrical discharge is used to create a plasma containing metastables, which then flow into our ceramic heater. So the heat aids in the desorption of the sample from the surface and helps with the ionization process. But before exiting the source to meet the sample in the open air, the plasma actually passes through a grid placed in the ceramic cap here that we can actually apply a voltage across it. So this grid voltage is applied to help prevent any ion-electron recombination, as the helium metastables are actually what drives the ionization process. So finally, ionization occurs out in the open air in front of the atmospheric pressure inlet of the mass spec. So from that ionization region, the gases are drawn into the mass spectrometer through the API to be analyzed. So a major appeal to DART mass spectrometry is its simple ionization process. So DART uses an ionization gas of either helium or nitrogen, with the user selecting the absorption temperature and sampling speed. So the range of the ceramic heater that we talked about earlier can go from room temperature, so about 25 degrees Celsius, all the way up to 500 degrees Celsius. And DART is a soft ionization process, like electrospray ionization. However, DART rarely forms sample ion clusters and rarely forms adducts. So we're not seeing sodium or potassium adducts. So given that the primary ion is going to be M plus H for positive ionization mode, or even M minus H for negative ionization mode. And as we can see in the figure on the right-hand side, DART works well with both nonpolar and polar analytes. It also best ionizes analytes under the molecular weight of 1,000, making it great for small molecule analysis. So what does sampling with DART actually look like? So there are two overall types of sampling with DART. And we kind of have a manual or an automated sampling process. So with manual sample introduction, think of directly inserting and ionizing a pill or a powder into that ionization region in front of the mass spectrometer. This is a common practice in the field of forensics for a nice, quick, and qualitative analysis. So here we do have a pill being held by a pair of tweezers, and we can directly insert it into that ionization region and ionize any analytes on the surface of that tablet. So with automated sampling, we can actually use a linear rail to move the sample into the ionization region, and also have the option for multiple samples to be analyzed at once. So here on the right-hand side, we have one of our most common modes of sample introduction. That's going to be our quick strip module. So here we have a linear rail driving a sample card into that ionization region. And we can ionize directly off the stainless steel mesh. Here's kind of a close-up image of that mesh. So we can actually deposit up to 12 samples, either solid or liquid, directly onto the mesh. And again, use that linear rail to introduce your sample into that ionization region. One of the benefits to DART is its modular design that allows us for diverse ways of sampling techniques. So here we just have a handful of ways that sample automation can be accomplished. So we already talked about DART quick strip. So kind of moving counterclockwise here, we have our 3D scanner. So this uses a second linear rail that allows us to raster across a surface. We have a 24-pin sampler tool. This uses precisely machined pins to collect a nanoliter level of volume. So we're doing sub volume sampling. We have our dippet module, so this allows for the accurate positioning and higher throughput of dippets. Dippets are just our glass capillary samplers. So you can ionize off of glass compared to stainless steel, depending on your analyte. And then lastly, we do have HTS DART, or high throughput sampling. This is similar to that of a quick strip. We were ionizing off of a stainless steel mesh. However, we can add a second linear rail to give us the option for ionizing larger sample cards. So these sample cards can now contain up to 96 or 384 samples compared to the 12 samples that QuickStrip offers. Now that we talked about the ionization source, let's take a moment to talk about the mass spec used in today's experiment. So the EVOQ Elite LC triple quad mass spectrometer is a robust system that can be swapped between DART and heated electrospray ionization within minutes. So this source does come standard with our heated electrospray ionization source for direct infusion, or if you're still trying to do LC-MS techniques. So that source is going to provide less thermal degradation and more sensitivity during analysis. And part of the robustness actually comes from the IQ dual ion funnel. So this ion funnel does not require DC current, so there is no impact observed on tuning parameters after running hundreds of matrix-rich samples. So hopefully saving you some time by eliminating the need for any retuning. So one of the largest advantages to the EVOQ triple quad is its sustained high sensitivity. So some problems that we see in various mass specs is kind of a signal roll-off due to the ion source getting dirty. So you're seeing a loss in productivity. And also, the cost of the ion source consumables, the ion source consumables being, different capillaries, glass, metal, you have to replace those, not often, but you will have to replace those eventually. So one of the features that we have, and some other mass specs have these as well, is in the orifice interface design. So ions can simply cross a plate, from ambient into our high pressure ion funnel, with a heated cone gas being applied to continuously flush the orifice to eliminate chemical noise entering the system. So again, we can see here, we have our ions being able to enter into the funnel with a heated nitrogen cone gas being applied to kind of help prevent any, particulates or chemical noise from getting into the ion funnel as well. So some of the added benefits that come along with, a system design like this is a lower cost of ownership. So again, we're not using any capillaries. There's less time spending cleaning the ion source, sourcing higher productivity, and then lower number of reassays due to that sustained higher sensitivity. So now that we have a handle on the hardware being used for today's webinar, I wanted to quickly introduce the use of solid phase microextraction, or SPME. Following this timeline, we can actually see that the hyphenation of SPME and mass spectrometry goes back to 1996. And following publication showing that SPME has been used in a wide variety of spray-based ionization techniques. And it wasn't until 2010 that there was one of the first reports of a coupling of DART mass spectrometry to SPME. And more recent publications have begun exploring the use of SPME in quantitative experiments. So because of the need to detect PFAS contaminants at such low levels, DART by itself doesn't stand much of a chance at ionizing PFAS samples in the low part per trillion range. So the use of SPME for PFAS analysis was a logical approach, given its ability to isolate and enrich analytes of interest within a sample matrix. Also, not only can the extraction phase of these devices be customized to optimally extract any desired analyte, but they can be designed to actually minimize the extraction of interferences. And different formats can also be used depending on the type of analysis. For example, and only to name a few of the many that have been published, we have a fiber SPME format and a blade format. So the SPME fiber, as the name implies, is a fiber coated at the tip here with your extractive phase. So there you have a small surface area available for desorption, and these fibers can actually be reconditioned for multiple extractions. However, one of the downsides is that these have proved to be more challenging application towards small volume sampling. So when looking at SPME blades, again, as the name implies, it's a blade-like device coated with your biocompatible extractive phase. So this blade has a larger surface area, which allows for greater sensitivity due to that increased level of desorption and ionization. You can achieve low detection limits just within minutes of extraction, and there shows a great potential for small volume spot sampling. And like the fibers, these can also be reconditioned for multiple extractions. So with all this considered, that SPME blades were actually used for this experiment. And as we can see in the upcoming slides, the pre-concentrating abilities of SPME for PFAS samples proved essential for DART mass spec analysis. So now looking at the sample preparation workflow for today's experiment, SPME blades were coated in a hydrophilic lipophilic balanced weak anion exchange particles embedded in a polyacetonitride, otherwise known as HLB wax pan. So this was used as our extraction phase. This was a technique that has been heavily explored by our collaborators at the University of Toledo. So here we have the workflow for the analysis of PFAS within a water matrix. So the first step is going to be your extraction step. So as the name implies, we're going to be using our SPME devices to extract our desired analyte out of the matrix. So in this case, we're going to be extracting PFAS compounds out of our water sample. So blades were placed in 1 milliliter of sample with agitation and agitated for 30 minutes. After that step, we move on to our desorption step. So again, as the name implies, we're going to be desorbing our analytes that were collected during the extraction phase and putting them into solution. So we're going to be taking the SPME blades, desorbing them in 250 microliters of 80-20 methanol water with 2% ammonium formate with agitation. And that's going to be a 20-minute process. So after that step, our sample preparation is actually complete. So we're able to do that in under an hour. So then we're going to take our desorption liquid and do 5 microliter aliquots for each of the samples in triplicate and spot those on the quick strip cards, that stainless steel mesh card that we talked about earlier, and allow those to dry. Once those are dry, those are placed into our sample card holder and analyzed by DART, and each ionization event is less than about 5 seconds a sample. And you can, of course, perform these extractions in parallel. So you can do the extraction and desorption at the same time, really just depending on the size of your agitator and the number of SPME devices. So the larger agitator, the more devices you have, you can actually decrease the time per sample and increasing your overall throughput. So I just wanted to jump ahead real quick for a second and talk about the type of data observed with DART mass spectrometry. So as seen in the quick strip below here, samples were spotted again in triplicate with a blank in between each set to monitor carryover. So looking at the chromatogram on the right, we have these 3 sets of peaks. And one thing about DART mass spectrometry, the data, when looking at a chromatogram, we're not thinking of these peaks as being compounds that are eluting off a column, so thinking retention time. We're actually associating each of these peaks with a sample spot on our quick strip card. So here we see 9 peaks. We have 9 samples that were spotted with 3 blanks. And that's going to be these gaps, in between each. So while we're, each sample spotting on the quick strip exhibited, nice profile shape and discrimination from the noise, it should be noted that we are seeing some variability, especially in, that 150 nanogram per liter calibrate level. However, this is easily corrected by the use of an internal standard. So seeing some variation in reproducibility with DART quick strip is common. And mainly that's because we are spotting these cards by hand. So if you're spotting a 5 microliter droplet, if you're spotting, placements a little bit different, that difference is going to reflect in your overall ionization. However, again, with the use of an internal standard, we can easily correct for a lot of these variations that we're seeing here. So here's just our MRM list of the different compounds we're targeting. We're operating our triple quad, negative ionization for analysis of these PFAS compounds. So we are just looking at 4 different PFAS compounds. We have PFOA and GenX. So we have 2 carboxylic acids, and then PFOS and PFBS, 2 sulfonic acids. So we're looking at 2 different classes of PFAS compounds. We're also using isotopically labeled internal standards to help correct for that variation that we talked about in the previous slide. So on the bottom here, we did run a 9-point calibration curve from 5 nanograms per liter all the way up to 5,000 nanograms per liter, again with an internal spike at 250. So to further push the response in SPME-DART for PFAS analysis, this highly sensitive technique must be developed with focus on the individual contaminant. So to accomplish this, a central composite design, or a CCD, was performed, and this allows efficient multivariate modeling of all selected independent variables, enabling not only the response optimum to be found, but also that the interactions between these variables. So the basis of the CCD is that the measured response is dependent on several factors which can be controlled in their operable conditions. So in our experimental design, we actually chose 3 variables that we can control on the DART. And that's going to be the plasma temperature. So how hot are we setting that ceramic heater? The grid voltage, so how many volts are we applying across that grid? And also the interface pressure. So we can actually control, how strongly are we pulling those ions in towards the API of the mass spec with the use of a small pump. Now, one thing to note, the pump didn't alter the results to that significantly. So, we kind of set that to an arbitrary value of -2. However, the plasma temperature and the voltage did influence the ionization. So we're going to talk about those a little bit more in detail. So taking a look at the CCD experiment for the carboxylic acid PFAS compounds. So these plots, we're going to take a look at the GenX one here on the right. It's a little bit easier to read the axis titles. So on this axis here, we're going to have our plasma temperature going from 50 degrees to 500 degrees, and the grid voltage on this axis here going from 0 volts to 400 volts. So the z-axis is actually the area response, so the intensity of the analyte detected. So the darker red in color is actually going to signify a stronger response, whereas a dark green color is going to signify a lower area response. So looking at kind of the apex of this, this curve up here, we kind of see a nice dark red color. So when looking at the axes here, we see that we're seeing a low voltage and kind of a mid-range temperature. So we have the voltage set now to actually 50 volts and 250 degrees for the heater for PFAS analysis. So when looking at the PFOA CCD experiment, while there was a little bit more room for adjustment on the temperature for PFOA, we're trying to create an optimal set of DART parameters for this class. So we can see that at 250 degrees and 50 volts, we're also still seeing a nice, strong ionization efficiency of PFOA. So it's with that in mind that we had the plasma temperature set at 250 degrees and the voltage across that grid set to 50 volts. Now, when looking at the sulfonic acid PFAS compounds, we see a little bit of a difference. So again, looking at PFOS here on the right, we have electric grid voltage on this axis going from 0 to 400, and then plasma temperature on this axis going from 50 to 500. So again, we can see low voltage is preferred in a nice dark red color on this corner here, and that's showing that PFOS is actually requiring a much more intense plasma temperature. And we're looking at PFBS as well. We're seeing kind of a similar response overall with a higher plasma temperature on this axis and a lower voltage on this axis here. So with the sulfonic acids, we're actually running the DART still at 50 volts, but now the plasma temperature is set to 400 degrees Celsius. So now that we have an understanding to how we're preparing our samples and our DART method, let's take a look at actually collecting some data. So I do have a couple screens pulled up here, and just to kind of walk through them pretty quickly. This screen here is just showing the mass spec parameters and the source settings and what they're currently reading and what they're actually set to. But on the right-hand side here, we have our DART control software. This is a web-based interface, so this is where we can actually input those DART parameters that we previously determined. So we can load that up into a pre-saved method to where you just need to hit just need to hit start to begin the analysis. Now the larger screen on the left-hand side here may look familiar, like your traditional LCMS batch table. So this is TQ Control. It's our control software for our triple quad. And while TQ Control probably deserves its own webinar to go over this piece of software, I just wanted to kind of show some of the highlights of TQ Control, being that this is kind of an all-in-one piece of software, meaning that we can do instrument tuning, mass spec method development, as well as batch management. So we can collect our data in this software, but we can also process it. So we can review data, we can quantitate data, and ultimately submit a report at the end of it. So you can kind of do everything in kind of a one-stop shop piece of software, rather than doing software or data analysis in one piece of software and data collection in another. So what we have here is our our batch table. So again, this may look like your traditional LCMS batch table. However, we just have 12 samples today, and that's going to correlate to the 12 sample spots on the quick ship card. So each, there is a communication between the DART and the mass spec. So we're able to collect each of those sample spots within its own data file. So just like you would an LCMS table, you can upload your sample conditions. You can submit your samples to be, queued in for injection, and then you can go ahead and hit start on the DART software. So there's going to be a little bit of a delay between hitting start and analyzing your first sample, and that's because we're in standby mode with the DART. So our heater is on, we're warmed up to 200 degrees, and now we're going to be flowing nitrogen through the source. So when you hit start, it's actually going to swap the gas out to helium. It's going to turn on that high voltage needle and begin generating that plasma. So we're going to be purging out that nitrogen, forming a nice stable plasma of that that heated helium. So once that 30-second passes and we're getting a nice stable spray or a nice stable DART gas stream, it's going to begin introducing your sample. And again, there's communication, so the DART can actually inject a sample onto the mass spec, and then we can watch kind of this real-time chromatogram, the data being collected. So we're seeing just a little bit of noise, and then ultimately what we're now going to see is a nice strong peak. So it's about a 5-second peak. We need a little bit of downtime on either side of the peak. So there's going to be, I think the mass spec method itself is about 18 seconds long, where the ionization event's about 5. So it's still a very quick process. It's much faster than a multi-minute LC-MS injection. But we're going to see a nice strong peak. And again, this is correlating to sample spot 1 on the quick strip card, rather than a specific retention time for a compound. So there's gonna the DART quick strip module is going to move on to the next one, queue in an injection, and keep the process moving forward. As you can see here, we're going to have the first one was our blank, the second one's starting to be our calibration, our level 1 calibration ran in triplicate, and it's going to move on to the following samples. Obviously, to kind of keep things moving along today, we're kind of just going to jump to the end. Now we are just looking at one quick strip card, and remember I had 9 calibrant levels, so I would just have to swap out the cards, put on card 2, put on card 3, and run those as well. So once the process is finished, we can then go ahead and begin analyzing the data. Again, still within the software. So it's a pretty quick process. We're able to do about all 12 samples in just under 8 minutes. All right, so looking at some of the data, we can see, we have some nice, strong calibration curves for these carboxylic acid analytes, so GenX and PFOA. And even looking at these insets, which is actually just a close-up range of the lower calibrant levels, we see that even the lower levels are still portraying, nice strong linearity. So we're getting limits of quantitation for PFOA down to 10 part per trillion, and GenX down to 50 part per trillion. So we're really pleased to kind of see this as a first attempt, a proof of principle response to our experiment. So looking at the sulfonic acids, again, we're getting some nice strong linearity. We're getting a limit of quantitation down to 50 part per trillion on PFOS and 25 part per trillion of PFBS. Now to kind of highlight the one thing we're probably all seeing is a larger error margin, or margin of error with PFBS. And this is partly due to the fact that we actually didn't have a labeled PFBS internal standard. We're actually just correcting off of the labeled standard of PFOS. And that's commonly a problem seen in PFAS testing, is not having of a labeled internal standard of all these different PFAS analytes, or even just a reference standard for PFAS analytes. So that either whether they're available or even just not really cost effective to be buying an internal standard for every analyte. So in future testing, we may be able to get one to kind of increase to reduce our variability observed, but again, we're still getting some nice strong quantitation. And again, just to also highlight, the elephant in the room, the limit of quantitations are not quite to the levels, that the EPA has put forth in their guidelines, and we're well aware of that. Again, we're trying to propose this as a robust quantitative method, or a way to, a high throughput screening device. So the end goal may be not to get, an exact quantitation. We're still going to be needing, LC-MS for some of these more sensitive samples. But the idea is if we can screen through these quickly to help reduce the amount of samples being analyzed by LC, would still be a very effective method. So to summarize here, we talked about a SPME-DART method that enables the rapid sample preparation of PFAS contaminants, and that the optimization of DART parameters allows for a more sensitive ionization and lowering the limits of detection. And again, just to kind of reiterate, the need for greater sensitivity is always going to be challenged as to keep up with the ever-expanding advisories. So the presented technique demonstrates screening and robust quantitations of these contaminants. And after the screening process, the samples are prepared in an LCMS accepted matrix. So we can actually take the same desorption solution that we prepped, take our 5 microlayer aliquots for DART analysis, and then take that solution and inject it directly onto a column. So this allows the user to be more, so using a screening process allows the user to be more selective and hopefully reduce the amount of samples analyzed by chromatographic techniques. So reducing the amount of injections you're putting on a column and producing less organic waste within your lab. So what's next for us here? We're going to continue expanding the list of DART optimized PFAS contaminants. In 2023, so this year actually, our collaborators at Toledo, they've already published a work investigating the same SPME devices, but extracting into an expanded 16 compound PFAS list. And we're also looking to increase our overall throughput. And we can do that by using our HTS DART setup. So again, we can do the same type of analysis, but now on a 96 or even a 384 sample format. And I think the biggest thing that we're excited to try is to collect these samples on our new EVOQ DART TQ+ mass spectrometer. So this is the latest piece of technology to come out of the Bruker Applied Mass Spec division. And this features the first fully integrated DART source on any mass spec. So we can see here on this left-hand side, we're now getting a smaller, more integrated DART source than what we currently are operating with. And as well as getting that, that DART source, we're actually seeing an improvement to the mass spec itself. So we're getting greater MRMs per second. We're now up to 1,000. We're getting a faster scan rate of 30,000 Daltons per second, ultimately giving you an increased sense of sensitivity, which is going to be crucial for PFAS analysis. And again, some of the benefits of using chromatography-free workflows is higher throughput, giving you a lower cost of operation, higher uptime, and reduced waste, reduced organic waste. And like our current system, it is just a quick, simple change, less than a couple minutes to go from DART to VIP Hezi to still do direct infusions and your traditional LCMS techniques. I just want to give a little notice to our collaborators at the University of Toledo. They actually published this work that I presented today in this year in the Journal of the American Society for Mass Spectrometry. You can go ahead and scan that QR code and it'll take you to that page. If you don't have access to that article, feel free to reach out, or we'll be more than happy to be able to provide some more literature or even some more information about PFAS solutions here at Bruker. And lastly, I'd like to thank you all for joining me on your day and listening to my talk. And I just want to give, again, a special thanks to Emanuela Gianfrido and her graduate students at the University of Toledo for providing the samples and the statistical analysis and overall the data analysis. So feel free to check out some of the work they're doing. They're really kind of pushing forward with the use of SPME devices in other areas than just PFAS. So again, thank you for your time. I believe we will have some time here for some questions, so I'd be happy to answer those. Thank you.
Thank you, William. Very exciting presentation. When William presented this at ASMS this year, it was standing room only, bright and early, 7 a.m. at that breakfast workshop. Very popular workshop, and now a very popular webinar too. So thank you very much, William. Now we will take some time to answer some of the questions you guys have submitted here. If you haven't done so, you still have some time. And I'd also like to note that when the webinar is over, you should receive an automatic email from the software with the recording. So if you want to go back, pause, reread, you do have that opportunity. So let's go through some of these questions you guys submitted. William, You mentioned that either helium or nitrogen can be used as the ionization gas. Did you try using nitrogen for analysis?
So we did. What's a common trend with DART analysis is that we tend to see a kind of a greater ionization efficiency with helium, and also kind of a reduced background with helium compared to nitrogen. So we did try using nitrogen just for the sake of, kind of moving forward with that helium conservation. However, we were seeing a more intense ionization process with helium over nitrogen. But again, as I kind of mentioned, we're now using helium only when we're introducing samples with, so in between sample analysis, we're actually conserving helium. When the DART method's done, it goes right back into standby. So now we're able to, kind of push forward with our helium conservation, and kind of stretch, a helium cylinder to last us, longer than it ever has before. So unfortunately, didn't quite work for PFAS analysis, but it is something that we tried.
Thank you. Is it possible to desorb the analytes directly from the SPME blades themselves?
So yeah, so kind of on that timeline slide that I showed, there's been a history of ionizing directly from the slides, whether it be a spray-based ionization technique or even inserting, the SPME fibers, directly into that ionization region within the DART source. However, again, it all kind of drives back to just the sensitivity needed for PFAS analysis. So to be able to kind of extract, the PFAS compounds that are spread out on that SPME blade, to be able to extract those into solution allowed us to kind of pre-concentrate it and kind of get the most, the most out of our, our 5 microliter droplet. So it is possible in some cases, but again, unfortunately, we did have to extract them into solution, for this experiment.
Okay. Is there any explanation as to why some analytes ionize better with a higher temperature than a lower temperature?
Yeah, so again, with DART, as a kind of a general rule of thumb, is that analytes with a larger molecular weight or boiling points tend to require, a higher plasma temperature to desorb and ionize. However, it was kind of noticed in this case is that, the carboxylic acid analytes, at that higher temperature with the, with the sulfonic acid analytes, they're actually starting to kind of thermally degrade. So we weren't just seeing the, the M-H ion, we were actually starting to see fragments associated with the increased temperature. So we couldn't quite ionize, the carboxylic acids at a higher temperature. But on the other hand, when looking at the sulfonic acids, at a lower temperature, it wasn't quite enough heat to desorb those off that stainless steel mesh. So yeah, there is a little bit of optimization needed to kind of find out what temperature desorbs your sample best. But in this case, we kind of had to split into 2 different classes and 2 sets of, ionization temperatures for the sulfonic and the carboxylic acids.
Okay, we have just a couple more here.
All right.
Have you tried the other matrices for PFAS analysis?
So for the study presented today, no. We just focused on water matrix. Again, this is kind of a proof of principle technique for the, kind of the coupling of SPME-DART for PFAS analysis. So we just focused on water for now. However, if you were to kind of go check out some of the work that the group at University of Toledo is doing, they're actually using the same SPME devices to do extractions within other matrices. So they're testing, food, environmental, and even biological samples because, kind of scarily enough, because of their, vast presence in our society or consumer goods, we're actually starting to begin to detect PFAS within, human blood. So something for us to try in the future, but unfortunately today it was just water matrices.
Mm-hmm. Does the plasma ionization generate ozone?
I don't believe so. I mean, I'm not too sure on that. I can certainly, kind of review it and follow up if you want to reach out. But as of right now, I don't want to give you a false answer, but I don't believe it does.
Mm-hmm. We can always reach back out to that attendee afterwards just to give them a confirmation. Can the same spot be rerun at the higher temperature?
No, maybe at the higher concentrations, yes, but unfortunately, even at the lower temperatures, there is some sample loss for the sulfonic acids. So what we found best, and again, because we're trying to get to those lower limits of detection, we found it best, we're doing 5 microliter spots, so we can just spot these cards twice and quickly run through them, under 2 sets of DART parameters. So yeah, unfortunately, we couldn't just rerun the same spot twice, once at a lower temperature and then again at a higher. We actually just went back through and, spotted our samples twice.
Perfect, thank you. And I believe that is the end of our questions. Very engaging audience today. Thank you all very much. If you do think of a question that comes to mind after the webinar, when you do get that automated email, you can respond and it'll go directly to myself and William. We can answer any other questions that come to mind, and we will follow up just to give you a confirmation on the ozone question. And thank you all very much for attending. We appreciate your time and hope you have a great rest of your day.
All right. Thank you, everyone.
Thank you.